This YouTube video will cover the flow simulation of an inline static mixer using computational fluid dynamics, or CFD. This will be done by me, Bailey Prey, and my partner, Daniel Guilbeaux. Computational fluid dynamics, or CFD, is the numerical study of fluid motion. The application of CFD is essential in the science, technology, and engineering industries, as well as many other industrial and non-industrial applications, in order to visualize how a fluid flows through or around a structure. CFD uses technology, such as a computer program, to study the flow of a fluid easily with little to no hand calculations. Engineering structures with intricate geometry and loads either have no theoretical solution or are very challenging to analyze. However, using CFD, a complicated structure can be easily analyzed. Commercial CFD programs are written so that users are able to solve complex mathematical problems without having to know the equations or mathematics surrounding the problem. By using CFD, the user is only required to understand the boundary conditions and geometry of the structure. This is great for complex problems where the calculations are difficult to solve by hand. The use of CFD can easily save both time and money and can help make modeling and testing a whole lot easier. This picture shows multiple different types of static mixers. A static mixer is a motionless, highly engineered mixing device that uses energy of a flow stream for an inline continuous mixing of fluids within a pipe. Static mixers are used for the purpose of cost-effective, consistent, and reliable mixing. They do not use any moving parts. They simply just create turbulence that increases the fast mixing of the injected fluid into the stream. These devices help to reduce space and to decrease the energy used for mixing. Static mixers are perfect for the chemical and petrochemical industries especially, but are used in many other industries as well. For this problem, we used a CFD program called ANSYS. When using this program, we had to sketch the mixer, then with the completed sketch, we generated it. This means that we basically made the sketch look three-dimensional, like an object would in real life. From there, we meshed the mixer. This is where we divide the object into multiple smaller parts using the computer. This is done to make the calculations easier in the end. Then we put the problem through a setup. We adjusted the boundary conditions or the constraints that were necessary for our problem to work. The edits we made were simple. Next, we initialized the problem. This is where we set up the problem to calculate from the inlet of the mixer and adjusted the velocity to match that of our inlet. Finally, we ran the calculations to finish the problem. From there, we took the pressure, temperature, and velocity contours. These are just colored figures to show how the pressure, temperature, and velocity are distributed throughout the model. Then we obtained an animation of the problem.
Here in our problem, we have two various liquids mixing in our inline static mixer. The first liquid is coming in at 0.4 meters per second and is at 353 kelvins. The second is also going to be coming in at 0.4 meters per second at 283 kelvins. So we're going to start by drawing a circle and we're going to extrude it 0.31 meters. Then we're going to draw a rectangle on each side and revolve them to make it 3D. These will both be in two inlets. Then we will draw a circle the same size over the base and extrude it up to cover the top of both of the inlets, as shown here. Next, we will draw a smaller circle that is 0.024 meters and we'll extrude it to 0.31 meters. Then we'll blend the edges. So to begin this meshing process, the first thing we're going to do is set the physical preference to CFD. Then we're going to set the element size and the max size to 0.05 meters. Then we will go to set an inflation on the body. We'll set the boundary for the inflation to everything except the faces that are on both of the inlets, the outlet, and the top of the mixer. We will then set the inflation option to total thickness with a max thickness
of 0.02 meters.
and then we will update the mesh. We'll then set name components by naming the two inlets, inlet 1 and inlet 2, and then the one outlet. Our fluent setup will be a parallel with a 4-level process. In models, we will set it to K epsilon at the realizable, and we will turn on the energy equation. Then at materials, we will create a fluent database, which will be water liquid. Then in cell zone conditions, we will go to solid, and then we will rename it water and set the material name as the water liquid that we copied. Then in boundary conditions, at inlet 1, we will change the velocity to 0.4 meters per second and the temperature to 353 kelvins. Then we will go to the outlet pressure and make sure that the gauge pressure is set at 0. And then we are set to run a hybrid initialization. After the hybrid initialization is complete, we can then run the calculation at 400 iterations. So we did 3 of our contours. This first one is our velocity contour. This second one is going to be our static pressure contour. And the third will show our temperature. We will now show an animation that will show the velocity streamline. So this will show what the velocity is doing when it's entering the inlets and what it's doing when it's mixing, and to show what it is doing through the outlet. This will show as particles are going through. This simulation shows the effectiveness that an inline static mixer can have over a traditional mixer that is gas powered or electric powered. There's a lot less upkeep on this, which ultimately will save you on costs. Also, these inline static mixers, upfront cost is a lot cheaper than the traditional. So in areas like this where it's not extremely heavy crude, it is a better scenario to use the inline static mixer over the traditional mixer.